In March of 1989, Earth experienced one of its strongest geomagnetic storms in modern history. It all started when scientists observed a cluster of sunspots, active magnetic areas on the sun's surface, emerging on its horizon. Over the next few days, the sun slowly rotated until the region began to point directly at Earth. Just as it did, 2 solar flares erupted from the sunspots. Accompanying the flares were coronal mass ejections, huge bursts of solar wind, essentially charged particles from the sun. The coronal mass ejections eventually crashed into the Earth's magnetic field, causing it to squish and compress and ultimately induce electric currents at the surface. In Quebec, Canada, the rapid changes in magnetic fields would have mostly gone unnoticed by people, but they didn't go unnoticed by the power grid. The region's unique geology, a shield of hard rock that's a poor conductor of electricity, kept these induced currents from dissipating into the ground. So they found another path, the electrical transmission lines. The geomagnetic storm ended up blacking out a large part of the Hydro-Quebec power grid for 9 hours. And the first domino of the collapse, or rather the first 7, were pieces of equipment known as static compensators. But to understand how static compensators work, and why a solar flare could trip them offline, you kinda have to start with the basics. You might know that most parts of all modern power grids use alternating current, or AC. The voltage and current on the lines slosh back and forth 50 or 60 cycles per second, depending on where you live. If you love power electronics, that low, dull AC hum might be music to your ears. But if this is kinda new to you, alternating current could be a little bit mysterious. What's even weirder is that even though the current constantly alternates its polarity, electrical power only moves in one direction, under ideal conditions. And geomagnetic storms aren't the only thing that can make the grid behave in funny ways. There are devices even in your own home that force the grid to produce power and move it through the system, even though they aren't consuming it. Let's go out to the garage and I can show you what I mean. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about how power actually flows on the grid. I built a model power grid here in the shop. Not the first time I've said that, and it probably won't be the last. I'll keep it simple at first and build up the complexity as I explain these concepts. And Zap McBodyslam is back in the shop to help out. My grid has one power source, right now just a battery, a transmission line to carry the power, and a load, in this case an incandescent bulb. It's probably not the most interesting circuit you've ever seen. But like I said, understanding the basics of power flow is essential to understanding the more complicated, and I think more interesting aspects of how it works on a huge scale. So here's a 1-minute refresher on electrical circuits. There are really only 4 numbers that matter the most in a circuit. First is voltage, the difference in electric potential between 2 locations. In the classic pipe analogy, voltage is the pressure that drives water to flow from one side to the other. In my circuit, the battery is supplying about 10 volts across this bulb. Next is current, the flow of electric charge. In the pipe analogy, this is the flow rate of the water. In my circuit, I can measure the current as 1.2 amps. Third is resistance, the opposition to the flow of current. It's the size of the pipe. Incandescent bulbs actually change their resistance depending on voltage, so it can't be measured directly with a meter. That's okay though, because all 3 of these values are related to each other. That relationship, called Ohm's law, is about as simple as it gets. Voltage is equal to current times resistance. If you know 2, you can find the other one with some basic math. For example, 10.1 volts flowing at 1.2 amps means the resistance of my light bulb is around 8 ohms. The final number we care about is power, the transfer of energy. Power does the actual work, in this case creating light and heat in the bulb. Calculating power is as simple as multiplying the voltage and the current together. 10 volts times 1.2 amps tells me this bulb is dissipating 12 watts. That's electrical engineering in a nutshell, and it's relatively straightforward for a circuit like this that uses direct current, or DC, because none of our important numbers change. But as I mentioned, that's not true on the grid. Let me swap out the battery with a transformer plugged into an outlet and see what happens. At first glance, there's no change. The bulb is still lighting, just like it did with the battery. I can measure the voltage by switching my meter to AC, 8.4 volts, not too far from the DC circuit. I can measure the current with this clamp over meter, 1.2 amps, same as before. But those are just simplifications of what's really happening on the lines. To see that, we need a different piece of equipment. This oscilloscope measures voltage over time and plots it as a graph on the screen. And I can insert a resistor into the circuit and use a second probe to plot the voltage across that resistor as a simple way of measuring current.
So the yellow will be the voltage, and the green will be the current.
You can see that neither the voltage nor the current are constant, unless you trip over all the cords.
Ah! Oh no.
They're switching directions over and over again. This might not be too surprising to you yet, but watch what happens if I switch out the light bulb with a different kind of load. Let's try a capacitor. This is a device that stores energy in an electric field between two plates. You see them everywhere in electrical circuits, and they do a funny thing on the grid. When I insert the capacitor into my circuit, the graph of voltage and current looks different because they're no longer in phase.
Hey, that worked perfectly.
The current waveform is leading the voltage. The current peaks happen before the voltage does. That's because the current has to flow into the capacitor before the voltage between the plates rises. It takes time for the capacitor to charge and discharge, which results in a delayed response in the voltage. Now let's try another type of load called an inductor. An inductor is basically a coil of wire. Like a capacitor, an inductor stores energy, but instead of an electric field, it stores that energy in a magnetic field. This is just an electromagnet like you might see in a scrapyard. If I swap in an air core inductor, you can hear the screwdriver rattle against the table as the magnetic field rapidly changes direction. And we get the opposite effect of the capacitor when the inductor is inserted into the circuit. This time the current waveform is lagging the voltage. That magnetic field resists changes in current, so it creates a delay, this time in the current waveform. I can even vary this inductance and thus the lag in the current by moving this ferrite rod in and out of the core. All this is interesting on its own, but these little shifts in a graph have serious implications on the grid and have even resulted in numerous blackouts across the world. Here's why. Remember that the power consumed by an electrical load is just the voltage multiplied by the current. We can do that for any point in time across this graph. For a purely resistive load like the light bulb, the current and voltage are in sync. When one is positive, the other is positive. When one is negative, the other is too. So when you multiply them together at any point along the graph, you always get a positive number. The power fluctuates, but it's always moving in one direction. For a reactive load, the term used for inductors and capacitors, that's no longer the case. There are times in the cycle when the current and voltage are opposite polarity, meaning instead of being consumed, power is actually flowing out of the load. In fact, for a purely capacitive or inductive load, there's no power consumption at all. No work being done. It's just stored in a magnetic or electric field and returned. But there's still current flowing, and that matters. Of course, most things connected to the power grid aren't purely reactive, but lots of devices that we plug in have some amount of inductance. Look around your home for any big motors. Air conditioners, refrigerators, washers, dryers, large power tools, and more primarily use induction motors because they're cheap, simple, and last a long time. And inside an induction motor is a series of wire coils used to create magnetic fields that spin the rotor, just like that inductor I used in the demo. Part of the power that flows into those coils just gets sent back out onto the grid. You might be thinking, so what? Nothing wrong with storing a little bit of energy as long as I give it back in less than a 60th of a second afterwards. But the grid still had to produce that power, and more importantly, deliver that power to your home and carry it back away. The electric meter at your home, in most cases, only tracks the power you actually consume, so you don't pay for the reactive power that flows into your devices and back out again. But that doesn't mean it doesn't come at a cost. It still has to flow through the power network, where some gets lost as heat from resistance in the lines. So the generators have to make, and the transmission lines have to move, more power. In some cases, a lot more power than is actually being used in the system. Reactive power can make up a big part of the total load on the system, even though it's not doing any work. Just having the infrastructure in place to handle it is also costly. The conductors, transformers, and generators on the grid have to be sized for the total current that needs to move through the system, not just the current that does work. And that stuff is expensive. It's like if you were a photographer and bought a bunch of props for a shoot from a company with a generous return policy. After you take your photos, you return everything back to the store. Those props were useful, even necessary to you, but only for a period of time. And there was a real cost to warehousing, transporting, and restocking them, even if you didn't bear it. Imagine if there were 100 photographers that did the same thing. It wouldn't be long before such a store wasn't very profitable. But unlike at your home, where the utility is generous in their return policy, lots of industrial and commercial customers do get charged for reactive power that uses up capacity on the grid without doing any real work. Even though the oscilloscope graphs just show a shift between two waveforms, with some clever math you can actually separate the real power being used from the reactive power that oscillates on the grid into two parts, and treat them like they flow through the grid independently. I'm going to do my best to avoid that math here, partly because it involves imaginary numbers, but mostly because it's not needed to understand the practical impacts. This is already a lot to wrap your head around. But out of that math comes this visualization. The power triangle. This leg is the real power that actually gets consumed, measured in watts or kilowatts that you're probably used to. This leg is the reactive power that's returned instead of used, measured in volt-amps reactive, or VAR. By convention, we usually say that inductive devices consume reactive power and capacitive devices supply it. The hypotenuse of the triangle is the apparent power, the total amount of power that flows through the grid, measured in volt-amps. If you divide the real power by the apparent power, you get this ratio, called the power factor, a number that will be important in a minute. Take a look at the distribution transformer that connects your home to the grid, and you might see a rating on the side. That number is not in watts or kilowatts like you might see on a toaster or microwave, but in kilovolt amps, because it includes the flow of real and reactive power. Large users of electricity, like factories and refineries, usually have a low power factor because they use a lot of big induction motors. They need comparatively robust and high-capacity connections to the grid, even if they actually consume only a portion of the energy that flows through. So the electric utility installs a meter that can track power factor, or they just come out every once in a while to measure it so they can put it on the bill. Instead of free returns on reactive power like we usually get at our homes, those customers have to pay a rental charge on the power they store, even though it goes right back out. But it's not just a matter of keeping track of costs. The stability of the entire grid depends on managing the flow of reactive power. If you've watched some of my other videos on the power grid, you know how important it is to closely match power generation with demands as they go up and down. If not managed carefully, the frequency of the grid, which needs to stay within a very tight tolerance, can deviate. And if it goes too far, the whole thing can collapse. That's what almost happened to Texas during the winter storm in 2021. But it's possible for the grid to collapse even if there's enough generation to meet the demand, because you still have to move that power to where it's needed over transmission lines. Engineers use a PV curve to keep an eye on this challenge. It relates the power flowing to a load on the system to the voltage it sees. As you would expect, the more power that flows, the more the voltage drops, since more power is lost on the transmission lines on the way to the load. It's the same reason the lights dim in old houses when the air conditioner kicks on. Current goes up, voltage goes down. If you combine Ohm's law and the power equation, you can see that the power lost on a transmission line is related to the current squared. Double the amps, quadruple the power lost as heat. But the further along this curve that the system operates, the more dangerous things get. There is a point, the nose of the curve, beyond which greater demand on the system actually reduces the amount of power that can be delivered, all while the voltage continues dropping. The generators may have the capacity to supply more power, but it can't reach the load because of the limitations of the system. Operating below the nose is unstable because generators lose control of their speed, like a rubber tire losing its grip on the road. Infrastructure is expensive, and building new power plants and transmission lines always comes with legal and environmental challenges too, so we're often forced to use the grid to the very limits of its capacity. But grid managers need to make sure to operate with enough margin that any contingency, like a generator going offline or a transmission line faulting, doesn't push the system over the electrical cliff. And here's where power factor comes in. Loads with lower power factor shift the nose of the PV curve down and to the left. That reduces the margin and lowers the voltages in the system for a given power demand, making voltage collapse more likely if some part of the system goes down. So we use several ways to supply reactive power to provide voltage support and shift the curve back up. Power plants can adjust their operating parameters to supply reactive power, but transmission lines have their own inductance that consumes the reactive power as it travels through. So it's usually more efficient to address the problem on the load side, and there are several types of infrastructure that make this possible. Synchronous condensers are big motors that aren't actually attached to anything. Instead of converting electrical power to mechanical power, they basically spin freely. But with some clever circuitry, they can generate or absorb reactive power from the grid. They can also help stabilize fluctuations in the grid with the inertia of their heavy rotating mass, something that's becoming increasingly important as we transition more to renewable sources that use inverters to connect to the network. Another option, and one you're more likely to spot, are shunt capacitor banks connected across the lines. Sometimes you can see them in substations, but many capacitor banks are installed on poles, out in the open for anyone to have a look. Like the capacitor in my demo, they increase the power factor and boost the PV curve up. That can actually become a problem during off-peak hours by boosting the voltage above where it should be. So many capacitor banks are switched on or off depending on system conditions. Looking back at the PV curve, you can see how leaving the capacitors off during periods of low demand keeps voltage within limits, and having them on when demand is high provides more margin and more voltage. Some run on timers to come on during the highest demands of the day, and many are operated at a utility's discretion to accommodate the varying conditions on the grid. They're usually either all the way on or all the way off, so deciding when to throw the switch is an important one. A third option for reactive power supply, called a static VAR compensator or SVC, addresses that challenge. These use electronics to rapidly switch inductors and capacitors on or off to constantly adjust to conditions in the system. That switching happens automatically and quickly, making them much better suited to the dynamic changes that happen on the grid. That's why Hydro-Quebec had them installed on their system in 1989. The long transmission lines between the hydroelectric power plants in the north and the load centers like Montreal in the south require careful control of the voltage to avoid instability, but the geomagnetic storm threw a wrench in the works. The induced currents in the transformers and along those transmission lines seriously increased the reactive power demand of the system. The resulting distortions in the voltage and current waveforms hadn't been considered when the equipment was installed. The SVCs weren't configured to handle the dynamic conditions affecting the system, so relays designed to protect them tripped, pulling the equipment out of service. Without the SVCs, the voltage on the grid dropped, the frequency increased, and chaos ensued. The grid operators couldn't disconnect customers fast enough to keep things stable, and within seconds, the rest of the system collapsed. Lots of equipment was permanently damaged, and millions woke up that frigid morning with no real power, reactive power, or apparent power, shutting down basically the entire province for half a day and requiring costly and expensive repairs. They learned a lot of lessons that day and adjusted a lot of relay settings since then. It's just one of the many case studies on the importance of understanding and managing this hopefully a little less perplexing idea of reactive power on the grid. One of the biggest challenges as renewables become a more significant proportion of electricity sources is controlling swings in voltage that can happen when the sun or the wind suddenly change. And one of the countries preparing to meet, at least for short periods of time, 100% of electrical demands using renewable sources is Australia. One idea they're exploring I thought was really cool is repurposing old fossil fuel generators into synchronous condensers that can stabilize those swings, keeping reactive power flowing. Pretty creative solution and pretty cool country. And if you want to see some of the coolest parts of it, my friend Sam of Windover Productions just kicked off the next season of Jetlag, a travel-based game show. They're going across the entire country trying to claim as many regions as possible by winning challenges. It's a super creative concept in its 10th season, and every episode gets released early on Nebula. You probably know about Nebula now. It's a streaming service built by and for independent creators. There are no studio executives deciding what gets the green light, no advertisements, and no algorithms driving the content into a single style. It's just independent creators making stuff they're excited about with as few barriers and distractions as possible between you and us. The website just got a huge update that completely redesigned the homepage, making it easier to find new stuff in addition to your favorites. My videos go live on Nebula before they come out here, and my practical construction series was specifically produced for Nebula viewers who want to see deeper dives into specific topics. I know there are a lot of streaming platforms out there right now, but there aren't many this cheap or where you know your money's going to support your favorite creators, and we have a 40% off deal right now. Pay just one time $30 for an entire year's access at nebula.tv/practical engineering. Or if you have subscription fatigue but still want to support what I'm doing, you can get a lifetime membership. Pay once and have access to everything Nebula will ever offer, including a bunch of very cool originals coming soon. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. Thank you for watching, and let me know what you think.